Now, the presentation here is a little unusual for me. I'm a researcher. Most of my presentations are about research that my group is doing. That's really not what this presentation is about. This is about work I did as a service to the profession back in the US. I'm a member of an organization called the Provisions Update Committee. Provisions Update Committee is the committee that drafts what's called the NEHRP Provisions and Commentary. Now, the NEHRP Provisions and Commentary, they come out about every 5 years. That is not a building code, but what it is it's the mechanism for bringing new ideas and research results into the code, vetting them, going through a long process to see if it's really viable, and then it goes into provisions. Provisions then become the source document for what's called ASCE 7. And ASCE 7 is pretty much the building code in most of the US. So as a county or a city or a state adopt a building code and make it law, they would be adopting a version of ASCE 7. So I don't get involved in the ASCE 7 part of it. That's really just fine-tuning language for legal purposes for the most part. Of course, there is additional expert review, but my job is with the PUC and mainly on issues related to soil structure interaction, site characterization, and ground motions. So with that as background, what I'm going to be talking about here are some pretty significant changes we made in the 2020 code cycle that became ASCE 7 in 2022. So they are now in ASCE 7. Even though it was published in 2022, it's not yet the code. That's just because there's usually about a 4 to 6 year window of time after publication before the code is actually adopted by different municipalities. But it's definitely on the way. And it has caused a bit of a stir, some of the things I'll talk to you about. So I originally prepared this presentation for a California audience. That was shortly after my arrival in February of this year. I then started talking to Professor Kubanowski, Professor Bradley, Dr. De La Torre about some of the things going on here. And then I understood that you all are also now moving towards a site classification approach that is using VS30, and that some of these same issues were relevant to you. And so it's for that reason that I'm essentially taking my earlier presentation for California engineers, taking out some very California-specific stuff and presenting it to you here, and I hope this will be of interest. I also hope that maybe this will help you New Zealanders avoid some of the problems that we've had in California. And that will be the subject of the last section in this talk. Okay. So this is my outline. I'm going to talk about site classes, and I'll be mainly emphasizing site classes that are defined based on VS profiles. We'll talk a little bit about VS measurements and VS estimation. It's very important to have a procedure that can be used even when you don't measure shear wave velocities, because some projects don't do that. And then this last topic, the depth range for VS30 calculation, may seem really obvious, 0 to 30, right? But as you'll see, it gets a little bit more complicated than that, at least in California, and that's where some of the pitfalls have occurred that I hope that you will avoid. So let's start with VS site classes. So I'll talk here about some historical approaches, which are actually not based directly on VS. I'll go into what are the VS, and particularly VS30 based approaches, and some of the problems with those approaches. It was those problems that we were seeking to address in our 2020 revisions, and so that's the new approach that's referenced here. So let's go through this. We want to go back in history a little bit for site classification, a real landmark document in the development of US building codes in all respects, from structural provisions to ground motions, is ATC3. ATC is the Applied Technology Council, still very active. It is what its name says. It's applied technology. It's doing research or taking research and really getting it into a form that practitioners can use it. This ATC3 document was really a landmark document from 1978 had many major figures in our field, Andy Valetsos, Nathan Newmark, Harry Seed, and others involved. On the ground motion side, one of the key people was Harry Seed. And he came up with the site classes you see here: rock and stiff soil sites, deep cohesionless soils, soft to medium clays. And what he's showing on the right, which is from a paper just a few years prior, 1976, are spectral shapes. So what's shown on the y-axis is the ratio of spectral acceleration to PGA. So it goes to 1 at 0 period, and then you see the shapes. And so this one here is rock, this is stiff soil, this is deep sandy soils, and this is soft to medium clays. Okay, so he's basically showing the different frequency contents of ground motions that are on different site conditions. An additional deep clays category was added in 1988. The reason for that was Mexico City had occurred in 1985, and that really had him pushing out the spectral shape to even longer periods. And an important detail of this is that the effect of the site condition at this stage was only on the spectral shape. The PGA itself was unaffected by site condition. PGA was mapped by the USGS, so the seismic hazard maps were PGA maps, that's it. And then you got your spectrum by attaching the spectral shape based on site condition to the PGA. So that was essentially the basis for our code from 1978, and then for about 14 years or so, or actually 16 years. A number of problems with that were understood as time went on, and a major update occurred in 1994. The Loma Prieta earthquake, which had happened in 1989, was a major motivator for revising and improving our seismic codes. In this 1994 NEHRP Provisions, VS30 was introduced into US practice. The sort of original idea for VS30 and the motivation for looking at it came from the US Geological Survey. So Bill Joyner was a major figure here, also Roger Borchert. And I'd like to just take a moment to define VS30, because sometimes details of its definition get confused. It is not an average velocity in the upper 30 meters. Okay, what it actually is a ratio of 30 meters on the numerator to the shear wave travel time through 30 meters in the denominator. So if this is your VS profile, notice it goes deeper than 30 meters. You basically only look at the upper 30 meters. You have 30 meters divided by the sum of the travel times through each of these velocity intervals here. So if we just look at this interval, we have a shear wave velocity for that interval of thickness. So the travel time through that interval is delta Z over VS. That becomes one of the travel times. We sum it up over all these intervals and we get VS30. That definition of VS30 was very intentional. When Bill Joyner and Roger Borchert formulated this, they were trying to give more weight in this averaging process to the slower layers, because it's the slower layers or the lower velocity layers that were thought to have the biggest impact on site response. Now, why did they do this? As I mentioned, there was work going on by Bill Joyner, work going on by Roger Borchert. I'm going to feature the Roger Borchert part of this here. And what Roger was doing was looking at data from different sites around San Francisco Bay that were reported in the 1989 Loma Prieta earthquake, and he was fitting some curves to it. The figure here is from a 2000 paper with first author Ricardo Dobry, but it's Roger Borchert's results from 1994. And I'll just highlight a few here. So he's showing here amplification versus VS30, and the red line is amplification for kind of mid periods, around a second. The actual range was 0.4 to 2 seconds, and averaging across, that range. And what you see is the amplification is going up as the VS30 goes down. He did another one for 1 second. Sorry, for short periods. This one is the 1 second, or the 0.4 to 2. The green one is short periods. That's 0.1 to 0.5 seconds. A good average is about 0.2. And that would be the green curve. And what he's showing is that in both cases, there is scaling with VS30, but the scaling is stronger for the mid periods than for the short periods. So as we go forward in time, we started to see ground motion models where the site amplification was based on VS30. So the NGA West project, which produced a series of ground motion models in 2008, and then a whole series of additional projects, NGA West 2, NGA Subduction, NGA East, have also used VS30 as the site parameter. And the way that the site amplification changes with VS30 is called VS30 scaling. Kind of the mathematical relationship is here. You have amplification in log units, the log of VS30 here. VS30 scaling is essentially the slope of this line. More amplification for soft soils, less amplification for stiff soils. And the slope in when you have a log VS30 axis is called C. So the larger C is, the more negative C is, the more the amplification you get. And this plot is showing kind of the range from different models in modern times for that slope C as a function of period. We see negative values throughout, but they are less negative at short periods, more negative at long periods. So the same general pattern that Roger Borchert was observing after the Loma Prieta earthquake, even with far more data in far more regions all over the world. Now, the way this was applied in the building code is the USGS did a national seismic hazard map for one site condition, and that site condition was 760 meters per second. That was the reference that had been recommended by Joyner and Borchert. So that's what they did, the entire country, one site condition. You would then look up your value of ground motion from a map like this. There was one for, this is 5 hertz or 0.2 seconds. That's called SS. There was another one for 1 second, S1, and another one for PGA. So you get these reference site ground motions. Then you use site factors, which were called FA and FB. These are what Borchert originally computed in 1994. And those site factors are linked to site classes A through E, with A being rock, E being very soft soil. This is the FA factors, and these are the FV factors. Notice the FV factors are larger numbers than the FA factors. That's because of higher VS30 scaling. And the fact that these are changing as we move to the right on the horizontal axis is indicating nonlinearity. So nonlinearity was not part of the code prior to this 1994 update. It was introduced in the form that you pretty much see here. In 1994, the nonlinearity was based on one-dimensional ground response analyses. So let's suppose you have 0.5 G 0.2 seconds and 0.2 G 1 second, and you have site class D. You would have a site amplification of 2 for FV and a site amplification of 1.5 for FA, if your site class is D. You now can construct the spectrum. You take the SS that's mapped by the USGS times FA, the S1 times FV, and you get SDS for short periods, SD1 for mid periods. That allows you to construct the building code spectrum, which was horizontal at short periods. That's SDS. It comes down as 1 over T through the ordinate SD1 at 1 second. Okay, and that comprised the spectrum that was used and still is actually the law of the land until ASCE 722 is adopted by different municipalities. Now, in that process, we have the site classifications A through E. This is the actual table from the NEHRP Provisions that provides that. So you see A is hard rock, B is rock, and so on down to soft clay. And these are the different boundaries. This is VS30. The code notation is VS with a bar. But there were also categories based on SPT blow counts and undrained shear strength. And you see there's a little bar over the top. So the little bar means it is a time averaged SPT blow count, and a time averaged S shear could be used equivalently to classify the sites. So that's what it was up to the time of the updates we did in 2020. The problems we were trying to fix is that N bar and SU bar have no physical meaning. I mean, who can explain what a time average blow count is, for crying out loud? That makes no sense, really. You cannot find any literature or any real justification for the values of blow count that go with the values of VS30. It's really just made up numbers based on people's experience and judgment. And in the framework that we had, if you're a geotechnical engineer, you don't need to develop a VS profile. There's no penalty for not doing it. You don't need to consider uncertainty in your site classification. So therefore, there's no penalty for not having a VS profile. And it essentially serves as a disincentive for a proper site investigation. We didn't think that was the way that the code should be structured. So the new approach, for one thing, we introduced more site classes. Now that was largely motivated by the fact that the USGS went away from these simple spectral shapes. They now have 16-point full spectra. And as you go to these full spectra, if you have such large steps between site classes, you can have large changes as you go from one class to the next. By going to 8 classes, we soften those boundaries. So we have 8 site classes now, plus site class F, which is special cases like liquefiable soils. These are the classes. So you see these kind of intermediate cases, B, C, C, D, and D, E, and so on, that have been added. And the ranges of VS30 in these different classes is narrower than it had been before. The big change that produced a lot of pushback, but we were able to get it through, is you now actually have to have a VS profile in order to classify your site. You can measure it, that's preferred, or you can develop the VS profile from correlations. So correlations are still allowed. But at the end of the day, you have to have a VS profile in your report, and then you're going to get the VS30 from that. Sometimes geotechnical exploration does not reach 30 meters. So we had to have provisions for how to deal with that. I know you have very similar provisions that are being put forward in the New Zealand code as well. So if the site exploration is not 30 meters, but it is more than 15 meters, and the geology is such that you don't expect deep or soft soils, you can just extend the last layer down to 30 meters and get a VS30. That is probably going to be biased a little bit on the low side. There are more rigorous ways of extending it that will account for the gradient, but those are optional. You don't have to use it. So the least effort approach would be to just extend the final layer down to 30 meters. If your profile is shallower than 15 meters, then you basically cannot classify your site, is the way the code is written now. And you have to use what are called default site classes. So the default site classes, you have to consider a whole range of possible site classes and envelope the ground motions. Those site classes that are enveloped are C, C, D, and D. So this process also, and I'll explain the details of how this works, it imposes a penalty when there is uncertainty in VS30 that will produce a range of possible site classes. So even if you've, say, done a CPT, you don't have a VS measurement, but you've done a good quality CPT, you developed VS from that, due to the uncertainty in the conversion from CPT to VS, there's a range of possible VS30s, there's a range of possible site classes. So there's a penalty built into the process when you do it that way. The penalty is there to account for uncertainty and to encourage the measurement of VS. We provided a commentary with a lot of specifics on how VS can be estimated from correlation relationships when it has not been measured. So let's take just a moment to talk about VS measurement. I should say that what I'm going to talk about here is not in the code. So the code basically says, go measure it. It doesn't prescribe how you should measure it. That is left up to the geotechnical engineer. What I'll talk about are invasive methods for doing this, surface wave methods, and then I'll conclude with some remarks about VS30 uncertainty. On the invasive methods, I think these are generally pretty well understood by geotechnical engineers, so I only have this one slide. You know, the general types of invasive methods are downhole suspension logging and crosshole. Invasive just means that you are invading the ground, basically. You are penetrating the ground either with a CPT or a borehole. The graphic on the right is for the case of downhole tests, either a borehole where we use geophones or a CPT with a geophone at the bottom. A nice way to present the results of downhole is to report travel times as a function of depth, like in a plot like this. And then what you can do is you can draw straight lines over different depth intervals, and the slopes of those lines are the velocities. So we have both VP and VS for the rivals of P waves and S waves in the test. That's a nice way to present the results so that you can, the reviewer can look at how you've interpreted the data and see if they agree with your layer boundaries and slopes. What's becoming very common in California, I'm not sure about New Zealand, but in California, surface wave methods are becoming increasingly popular for measuring shear wave velocity. But the thing is they don't actually measure shear wave velocity. And so I want to emphasize what they actually do measure and some of the different methods for doing it. So in the example I'm showing here, there's two receivers. There's one source. It's usually shaking vertically. It's producing surface waves that are traveling along, and the wave arrives at this receiver before it arrives at that receiver with the distance s. What's being measured is a Rayleigh wave phase velocity that is essentially the ratio of the spacing divided by the travel time between the two receivers. That Rayleigh wave phase velocity can be equivalently expressed as a frequency times a wavelength. So if you know the frequency of the excitation that you're using and you have the Rayleigh wave phase velocity, you can calculate the wavelength. And for one spacing and one frequency, you get one data point in a Rayleigh wave velocity versus wavelength plot. If you basically repeat this by cycling through many different frequencies and using multiple spacings of the geophones, you can get a whole series of points in the space, and that is called a dispersion curve. So one of the key points I would like to emphasize here is that if you're using surface wave methods, it is the dispersion curve that you're measuring, and the dispersion curve should be reported in the geotechnical documentation, because that's the measurements. Now, there are a number of ways of doing this. My graphic was for an active source and two geophones. That is called spectral analysis of surface waves. SASW is kind of the classical way of doing this. There are more modern methods that use an active source and multiple geophones, MASW. And there are passive methods that don't have any source. They're usually circular arrays, and you're basically reporting waves traveling across the array that can be coming from any direction. That's why you need a circular array, and those work fine as well. So there's really no problem in the view of our working group to use any of these methods here. There is one method, however, that is not recommended, and that is REMI. Again, I'm not as familiar with New Zealand practice on these things, but REMI is a method that comes out of a group in Nevada. It's become very popular. It's a passive method with two sensors on a line, and it doesn't work very well. It can work. You can find cases where it works fine. The problem is essentially if your two sensors are like, let me do it horizontally like this, if the wave is coming this direction, there's no problem. But if the wave is coming this direction, it appears to arrive at the two sensors at nearly the same time. So therefore, it appears like the velocity is really high when it really isn't. It's just a wave directionality thing. You get around that problem by having a circular array. REMI doesn't use a circular array. It uses a two geophone array in a line. And if your energy is preferentially coming from a particular direction, you can't tell that that's the case, and you're going to get a high velocity. So it tends to produce biased high phase velocities, and that is a problem. So it's not recommended. The VS profile can be inverted from dispersion curves, because remember, VS is what we want, but we're not measuring it. So we invert it through a process that is non-unique, meaning that multiple shear wave velocity profiles can be derived for a given dispersion curve. And it is recommended to do that, to sample many possible profiles that would match the dispersion curve. So that's shown for an example site here in Los Angeles. This is the same set of profiles, just this is going down 50 meters and this is going down 1,000. And you can see how the uncertainty is growing as you go deeper into the profile. So best practice would be to show multiple inverted profiles, calculate the VS30 from each of them, and then have some representation of uncertainty. On the subject of uncertainty, when we measure VS, there is some uncertainty in the VS30 value. The reason for that is that if you measure it multiple times at the same site, you will get slightly different values. And so if you essentially calculate the dispersion of that, it's not zero. We were well aware of that as we wrote these provisions, but ultimately we said that you don't have to concern yourself with VS30 uncertainty when you make a measurement that goes 30 meters. So there is no formal consideration of that. My understanding is the New Zealand provisions take a different approach. There is a small uncertainty that you have to consider, but we don't have that in the US code. We reserve the uncertainty argument for this case, which is the VS estimation. So I'm just going to go through how to estimate VS, some general concepts. We'll talk about relationships that use penetration resistance. I'm going to actually skip the example local relationships because that's really California specific. And then I'll talk about the uncertainty. So VS, it's a soil property and it has a relationship with lots of other parameters. So that gives us the opportunity to measure something else and try to infer VS from the something else. So one of the things it has been related to in literature, particularly for clays, is the undrained shear strength. So you might have a relationship like this for Holocene soils. We have exactly these types of relationships in California, and maybe a relationship like this for a compositionally similar material, but just older, like a Pleistocene material. These models tend to be region dependent. So we have relationships that apply to geological units in the San Francisco Bay Area. We have other ones that are appropriate for Los Angeles, as you see here schematically. And different variables may be used for different soil types. So what I was showing before was undrained shear strength. We have other relationships for void ratio, for example. So you take some relationship, and this could include penetration resistance-based relationships, and we're going to estimate the VS profile. So I'm going to walk us through this process schematically. We, in this case, measure the void ratio. So we have the blue measurement points, which are a shallow layer, maybe a normally consolidated softer material. The red data points deeper, might be an older, denser material. So that's the measurements. And then we're going to come up with the VS by using a relationship that maps void ratio to shear wave velocity. When we go to VS, you'll notice the little horizontal lines going through there. Those are representing the fact that while the void ratio doesn't have much uncertainty, the VS does due to the correlation that we're using. Once we have that VS profile, we can calculate a VS30 just in the conventional way. And there is some uncertainty in that relationship, but what you'll see is that the uncertainty in the VS30 from these correlations is smaller than the uncertainty in the VS at a given depth. So uncertainty in the VS at a given depth might be in the range of 0.15 to 0.3 or so natural log units. The uncertainty in the VS30 tends to be smaller than that because there's some averaging that goes on. Maybe VS is high in one location and low in another. It kind of averages out a little bit so that we have pretty favorable VS30 uncertainties, as shown here. So that's all very schematic in general. In the commentary of Chapter 20 of the NEHRP Provisions, in commentary documentation, we have some specific guidance on inferring VS from penetration resistance. So this is kind of a very general form of the equation that you can find in a whole series of modern relationships. We have the natural log of the VS. This is a coefficient, a second coefficient that scales the log of the penetration resistance, a coefficient that scales a term related to depth, and then we have an error term over here. Okay, so natural log of VS penetration resistance. So that would be like N60 or tip resistance normalized by atmospheric pressure. It is not overburden corrected. Okay, so the modern relationships will not apply an overburden correction in the penetration resistance because that comes in separately through the C2 term. So the way that, say, blow count changes with overburden is not the same as the way that shear wave velocity changes with overburden. So that's why we have to have a separate term in here. Well, let me just go back. So the shear wave velocity will increase with increasing penetration resistance. So C1 terms will be positive. VS will also increase as overburden increases. This overburden can be depth, effective stress, like sigma V prime, or mean effective stress. As this goes up, shear wave velocity will go up, so C2 is also going to be positive. This epsilon is just the standard normal variate. So if what you want is the mean, you set epsilon to 0. If you want the mean plus 1 standard deviation, you set epsilon to 1. And the sigma is the uncertainty in the relationship. So the relationships are going to give you C0, C1, C2, and sigma so that you can apply it. So one such relationship that was developed for data using data from California bridge sites is Brandenburg et al. 2010. That relationship has each of these coefficients dependent on soil type. So sand, silt, clay, you see the different coefficients here. These are different kinds of error terms. One of them is the uncertainty within a borehole, and the other one is the uncertainty between boreholes. So that is broken out differently. The two uncertainties are combined through SRSS to get the overall uncertainty sigma ln Vs. In New Zealand, CPT is super popular. And it's pretty popular in California as well. So probably for the most part, these relations will be used with CPT data. In that case, this equation is written a little differently. The main thing that changes is this term here, which brings in soil type. So in the SPT relationship, you had soil type through the coefficients themselves. In the CPT, these coefficients are fixed, and soil type comes in through this term right here. And that FM term is a material type parameter, can be friction ratio, IC, or something like that. Otherwise, it's constructed in the same way. These are several models that we specifically referenced and provided. We essentially took the coefficients the authors provided, and we presented it in this sort of uniform framework that I've just described. One of them is Hegazi and Main. Another one is Andrus et al. 2007. And one of them is a model here from New Zealand, McGann et al. 2015. And this is just showing what depth term these models used and what soil type term the different models used. And this is the summary table for what these coefficients are for each of the models. The note here at the end is just how they treat uncertainty. And basically, most of them don't treat uncertainty. So note A means it doesn't exist in the model. But note B for the McGann model describes different uncertainties for different depth ranges. Okay, so we have VS30 uncertainty. It's considered in the assignment of site class when VS profiles are estimated and not measured. So we needed to provide some guidance on this subject for practitioners using these correlations. So the way that this was approached, we actually accessed a couple of different studies from literature that had considered what is the VS30 uncertainty when it is estimated with correlation relationships. So there was one study that had been done in Japan. So they developed specific relationships for Japan to get VS, then used those to come up with the VS30. Same thing in California. These two models use similar functional forms. The Japan model also considers geologic age. So it's like the Brandenburg model I showed, but with geologic age considered in the coefficients as well. Essentially, what was done in these different studies was you take sites where you have a measured VS, you calculate the VS30 from the measured VS profile, you calculate VS30 from the estimated VS profile, and then you look at the statistics of the differences. Okay, so you have those two sets. We calculate the difference, which is this natural log delta here. It's the invasive-based VS30 minus the SPT-based VS30. And what we find is that the sigma on these things is pretty close from the two studies, 0.22 to 0.26. So that motivated this clause in the building code, section 20.2. I'll just read it. Due to the uncertainty inherent to such correlations, site class based on estimated values of VS30 shall be derived using VS30, VS30 divided by 1.3, and 1.3 times VS30 when these correlations are used. If these different average velocities result in different site classes for the site class table, the most critical is used for a given period. So what that basically means, as I'll illustrate, is you have to envelope the spectra for the three site classes, if there are three. Why is the factor 1.3 here? Essentially, if you take the exponent of 0.22, you get 1.24. If you take the exponent of 0.26, you get 1.3. So 1.3 seemed like a reasonable characterization of these results from the literature. So just to give an example of how this works, this is a CPT profile, QT, friction ratio, VS over here. So you have the different thicknesses of layers, the different VSs. These are travel times. This is the sum of the travel times. So 30 meters divided by that is 154 meters per second, 506 feet per second. So that in our table is site class DE. 154 is between 150 and 210. However, this is a specific thing that we have in our site class. I don't know if you have this here. I think maybe you don't. We come back to this log again. You'll notice that there's a very soft organic silt and clay layer with a high PI and a fairly high water content. Being a soft clay, there is a criteria for site class E that says, regardless of the VS30, if you have more than 3 meters of soft clay, and in this case there's 3.5, then it would actually be reclassified as class E. Okay, so let's just forget about that for a moment. Let's suppose that it is DE, and let's suppose that the 506 were from an estimated, not a measured VS. So the rule that I described earlier, you would have to develop spectra for 506, 506 divided and multiplied by 1.3. So you see the velocities here. That's going to lead to different site classes. So if we ignore the special provisions for class E, the classes based on these velocities would be DE, DE, E, and DE again, so DE and E. And so we would develop multiple spectra. So we would have a spectra like this for DE, a spectra like this for E, and we would envelope it. So that means at every period, you take the maximum value from the two individual spectra. So that is imposing a penalty inherently in that process by being conservative and enveloping. Okay, the last topic I would like to discuss, and this is the pitfall I referenced earlier, is the depth range for the VS30 calculation. So I'll talk about what the provisions now specify about this issue, talk about why this change was made. I'll talk about ground motion estimation for basement levels in buildings, which is where this becomes an issue, and application of site-specific procedures. So what the provision states, and some of this language was specifically added in 2020, is the soil site shall be classified in accordance with Table 20.2-1 and Section 20.2 based on the average shear wave velocity parameter. That's all the same as before, which is derived from the measured shear wave velocity profile from the ground surface to a depth of 100 feet or 30 meters. This is the key part at the end here. That specific depth range was added in the 2020 provisions. And so kind of the obvious question is, why did we feel the need to define that depth range when that has always been what everybody has taken it as? Going back to Bill Joyner in 1992, all the way to the present, any model that uses VS30 always uses that definition. Seems kind of obvious. Why did we have to state the obvious, basically? Well, one reason why we felt that we had to do it is that the 0 to 30 definition is what is used everywhere, like I just said. So back to the origins of the parameter, there has never been any other definition of VS30 that has ever been used in any kind of scientific literature. So if that's the definition, and if you have ground motion models that are being derived from ground motion data, and if those data are regressed against independent variables, one of which is VS30, the principal variable representing site condition is VS30 in these ground motion models. So where does that VS30 come from that goes into the ground motion models? Well, it comes from VS profiles in some cases. And those are, the VS30 is from 0 to 30 meters. It is from proxy-based relationships. In other cases, proxy relationships are where you only have surface geology, for example, and you use that to estimate VS30. Well, those proxy relationships are based on measured VS profiles, where the VS30 is taken from 0 to 30 meters. So I know I'm being a little bit redundant here, but I'm just trying to drive home the point that the ground motion models that we're using to predict ground motion use VS30 defined a particular way, okay? And so they return values that are based on that definition. You should not apply them with a VS30 that is derived using a different definition, okay? And that's essentially the issue. So that's kind of the obvious reason why we should use 0 to 30 meters. The less obvious answer, which is the source of the problem, is that recent practice has developed in California and probably elsewhere. I know it occurs in Seattle, Portland, places like that as well, to change the VS30 definition for embedded structures. So here's a structure, it's embedded a depth ZF. This is the motion we're trying to predict, and this is the VS profile for the site. So if that's 30 meters, that is your VS30. Okay. The recent practice is to say, no, what we're actually going to do is we're going to take the starting depth at the base of the foundation. We're going to go 30 meters down from that, and we're going to use that to get VS30. And in order to avoid confusion, I'm going to call that VS30 star, because it's not really VS30, it's this sort of modified VS30, measured from foundation depth to foundation depth plus 30 meters. The stated intent of the practitioners who do this, and they do it repeatedly, is to define ground motions that are applicable at the foundation level of the structure. Their argument is, after all, nobody cares about the ground motion up here. What we want is the ground motion down here. So we're going to use the VS30 from that depth downward. If you don't think about it too much, that makes sense. That is the base of the structure, after all. Why don't we just use that? Well, I don't usually use language this direct and sort of rough, but here it is. This practice is incorrect without any qualifications. It is incorrect and it is unconservative. Let me explain why. When a GMM site factor is used, it is based on VS30 from the standard definition. VS30, of course, it's only measured over 30 meters. But the truth is that what you measure over 30 meters has a surprising degree of correlation to what happens much deeper. And this has been shown by Dave Bohr and others. You look at these profiles here, these are the average profiles for 380, 270, and 160, and you see they have different gradients. You see these profiles go down much deeper than 30 meters. What you get, for example, with a 380 profile at large depth is different than what you get in a 270 profile at large depth. The point is that what you get 100 meters down 300 meters down, even a kilometer down in these deep basins, has a correlation with VS30. And that's important because while 30 meters does not control site response for very long wavelength ground motions, because of that correlation to the deeper structure, the VS30 does have predictive power. And as I explained earlier with Roger Borchert's results and the more recent results, in fact, the VS30 scaling, this is kind of a paradox, but it's there in the data. VS30 scaling is much stronger at long periods, where the wavelengths are much, much bigger than 30 meters, than it is at short periods, where the wavelengths may be close to 30 meters. That would not be the case if it wasn't for this very strong correlation. And this is an example, for 160, look how much stronger the amplification is out here at 2 seconds than it is down here at short periods. And these differences in amplification are largest at the long periods. Okay, so let's now look at it a slightly different way. VS30 star is going to be greater than VS30 almost all the time because of velocity gradients increasing with depth. So if this is VS30, this is VS30 star, bigger number. Again, all the GMM knows is the standard definition. You could make a you could make a GMM based on a different VS definition if you wanted to, but we don't have GMMs based on that. We only have GMMs based on the standard definition. So if you plug in a different VS30 than the actual VS30 for your site, the GMM is going to think you have a different site than the one you actually have. So what the GMM is going to think is that the VS profile, this red one, is what goes with VS30 star. And as we see, it's quite different, even at large depth. So what happens then is that the different profile is going to have a reduced site response than the real profile. And the difference in the site responses is going to be most pronounced at long periods. So if this is the spectrum you would get using the site response for VS30, this might be the spectrum you get when you use VS30 star, okay? So what consultants are doing is getting the red one when the real ground motion should be the blue one. So we put the specific definition in there to make this practice hopefully go away. Now, the consultant's argument that we don't care about free field ground surface motions, we want motions at the base of the structure, is a very legitimate concern. There is nothing wrong with wanting to do that. Modifying VS30 is just the wrong way to get to your objective. The right way to get to your objective is there's several possibilities. So one approach is you apply your site factors within the GMM using the actual VS30. Then you get your ground surface motions. You then modify those motions down to your foundation. So you go from here basically down to here, and you're using soil structure interaction principles. Those principles will tell you that at a long wavelength, like this one, this will not be reduced very much from the ground surface. But for short wavelengths like this one, there will be an appreciable reduction of this one relative to the surface. So there are relationships for this that are in literature. They're also in different chapters of the building code that you can use. This is essentially what they give you is this transfer function here, where as you go to larger values of period or shorter wavelengths, larger values of frequency or shorter wavelengths, this transfer function ordinate goes down to a lower bound of about 0.5. So that's a legitimate way to reduce the ground motion. It's going to have virtually no impact at long periods, and it's going to have a reduction at short periods. Notice what I just said. It'll have virtually no impact at long periods. Exactly the opposite of what the VS30 redefinition does, which has the most profound impact at long periods. This makes a really big difference for tall buildings. So this is reducing the short periods, but not the long. A second approach is if you're running ground response analysis, so you're taking waves and bringing them up through your site with a code like deep soil or something like that, you can certainly do that. and you can output the ground motion as an outcropping motion at the depth of your foundation. That'll be a different ground motion than if you carried it all the way to the surface. And conceptually, this is basically the same thing as the soil structure interaction approach. It's just more specific to your site because it includes your site-specific profile. And that, again, will produce virtually no difference at long periods, and it will produce a difference at short periods. If you do this approach, which is allowed in the code, you should not also apply the SSI adjustment because there are basically two ways of doing the same thing. So you do it one way or the other. Okay, so I'm going to wrap up now. We've had pretty major changes in ASCE 722 and the 2020 NEHRP provisions. Many of what we put into these documents are in your document. I have read your document, and I see a lot of the same language. So a lot of what I've talked about did carry right over into the New Zealand standards. So we have site classes that are now defined solely based on VS profiles with Class E and Class F exceptions. As far as I know, you're doing the same thing. You don't have blow count-based site classes. You don't have under-end shear strength-based site classes. When the VS profile is estimated, uncertainty in the resulting VS30 is considered in assigning the site class. You're doing the same thing. In fact, you do it in an almost identical way to the way that we are doing it. The depth range for VS30 calculation is defined. This was a big deal for us for the reason I just explained. You just say it's 0 to 30, which is fine. That is what it is. And hopefully you don't go down the path of having bad practices as we have had, because once you start down a path like that, it's very hard to reverse course and change things. When we put this out, the way this process works, which is also the way your process works, we put it out there. There was a public comment period. We got all kinds of objections, okay? Those objections said, requiring a VS profile is way too complicated for simple projects. You guys are being you're being too academic in your approach in requiring all of this. And there was pretty strenuous disagreement with not allowing VS30 star. The way that our process works is people can say whatever they want. We're going to consider it. We're going to hear the public comment. We're going to talk to folks. But in the end, the people on the committee, for better or for worse, decide whether it's persuasive. We found these arguments to be non-persuasive. So the provisions, as I just described it, are in the NEHRP 2020 and also in ASCE 722. So that's pretty much all I have to say. I wish you the best of luck as you venture into the wonderful world of VS30 and start using it for your site classifications.